Hi everyone, my name is Như Nguyễn from group number 3. Today I will talk about our research topic, distributed learning and its application for time series prediction. First of all, let me introduce the background and challenges in our work. Our work have two sessions. The first session is about extreme events and the second session is about distributed learning framework. From literature reviews, especially from statistical area, we see that extreme event reason in time series data is an important topic. However, they are not carefully considered or analyzed in time series prediction applications, especially from the perspective of computer science. Moreover, current predictors are largely built using deep learning models. It means that these models take a long time to train, especially on a single compute node. So this is the reason why the distributed learning frameworks come in. However, the traditional distributed learning framework require a large amount of communication costs and synchronization costs. Moreover, we want to do a sensitivity study on what kind of information it can to have accelerate the training process. So our work use the asynchronous distributed learning framework for time series prediction. And we use the linearly increasing sample size sequence, which will be described in the following slide to reduce the communication cost. And we also pay attention to extreme event to see the impact of the events to the performance of time series prediction. Before zooming to the system design, I want to briefly talk about the related work. For the distributed machine learning, we have synchronous setting and asynchronous setting. Compared to the synchronous setting, the asynchronous setting can fully utilize the capacity of compute nodes. However, it's hard to implement and analyze. When I mention the analyze here, I mean it's hard to prove the conversion rate or the conversion reality of the asynchronous setting. We also want to talk about the periods when the information is changed among compute nodes. We can exchange the information for every HGD iteration, for certain of HGD iteration, or when a specific threshold is triggered. For the linearly increasing sample sequence, is the adaptive local HGD. There are a list of reference papers here about the distributed machine learning, and if you have an interest, you can take a look. For the time series prediction, we have some traditional methods, for example, ARMA and RX. And when the deep learning method comes in, we have the RNN model. To deal with the extreme events, we have some sampling methods. You can take a look at some common methods from the reference paper 6 here. This is the system design of our distributed learning framework. We use the client server architecture, and each client or compute node here runs local HCD. And after that, the local model from each client is sent back to the central server for aggregation. The chain process here can be synchronous or asynchronous, depend on the settings, but we want to achieve the synchronous setting here. Uh, We have multiple RNN models from RNN STM to RRU with or without tension. So here we choose the RSTM model for time series reason application. Moreover, we choose the sliding window, which needs to be large enough to cover the extreme events and to achieve decent performance. And we use the L2 regularization to help reduce the overfitting, especially for the extreme event sampling method. In order to model the extreme event, our work motivated by the extreme value theory. It focuses on the extreme deviation from the median of probability distributions, and it used the heavy-tailed distribution. To summarize the ideas of our work, there are three main points here. In order to reduce the training duration and to fully utilize the Communus, we use a synchronous distributed learning framework. And to reduce the communication cost, we use the linearly increasing sample sequences. You can see the example here, which show the effectiveness of the linearly increasing sample sequence in terms of the communication routes. And to exploit the extreme events, we use the extreme loss function. I will briefly talk about the experimental setting here. Our experiments are conducted on the Linux 64-bit operating system. The main programming language are Python plus PyTorch. The dataset here is S&P 500 stock in the branch of 5 years. And we compare with the baseline. Here is the LSTM model run in the single computer in terms of the prediction accuracy and the training duration. Here, the figures here show the result of distributed learning with two computers compared with the baseline one computer for Apple stock. When the step increase or the SGD iteration increase, we see that the prediction for two computers and one computer gets closer and closer to the route truth. Here, the experiment for 5 computers and 10 computers, and it showed that our distributed learning framework can achieve the same level of prediction compared to the baseline. Uh, in this slide, we summarize the speed up ratio for different number of computers compared to the baseline. Here we see that the speed up ratio is considerable. However, the central server need to aggregate the global model from computers. So it made the speed up less than the number of computers. And the results confirm that there are speed up saturation in the distributed learning frameworks. And in practice, some other methods need to be considered to remove the limited speed up here. I mean, we want to increase the upper bound of the speed of saturation. So in this work, we successfully implement the distributed learning framework for time series regression using linearly increasing sample sequences. And we also do a sensitivity study on the extreme events. However, the extreme event loss is not integrated to our model yet. and I hope to do this in the future work. And moreover, the data set here is quite simple. We will figure out other time series datasets and rerun our experiment. This is the conclusion and our future work. Thank you.